I'll be explaining about the Jordan normal form. This whole video will go through the topic Jordan normal form, and for a brief introduction of what this is a easier way to write a square matrix so that it would be easier to work with the matrices. So the thing is, matrices in linear algebra is used for like transformation, rotation, reflection, you know that. But in dealing with matrices, the easier form is considered to be a diagonalized form. Like you should remember while solving any equations or even converting some equations into augmented matrix, you the very first step is to convert the matrix to a diagonalized matrix where the elements except the diagonalized values are zero, so that it will be easier to compute the values, right? So uh, that's the thing. The diagonal matrices are easy to deal with because these matrices are simplest to work with because all the entries of the main diagonals are zero. So if you either do power multiplication of this matrix, it's easier to uh, anticipate what the outcome will be. And there are various practical advantages of this, like many matrices cannot be also diagonalized. That's a problem. Like every matrices are not diagonalized or cannot be diagonalized, and that's a problem, and this is why we exactly need the Jordan normal form. So it's not a complex topic. The topic is just about how to make the matrices in a easier form or a closer to diagonal form so that it would be easier to work with those matrices, right? So let's go a little bit deep into why Jordan normal form is needed. Before diving deep into what is eigenvalues, what's eigenvectors, and why these things come out, what I want to revise is mm, matrix has various applications inside linear algebra, outside linear algebra, and especially in this, let's focus on inside of the linear algebra. It's used for transformation. It's used for rotation, reflection, and all those things. So for that, the calculations of regarding matrices are very important. Most of the matrices are converted to diagonal form and work with it. However, many of the matrices cannot be converted towards or diagonalized form. So the nearest diagonalized form that can be converted to is the Jordan normal form. Like for example, let's inside of linear algebra, let's consider a matrix. So there is a matrix A equals to there is a matrix, and here the eigenvalue appears twice, but we'll see there's only one independent eigenvector. For learning this Jordan normal form, a clear understanding of eigenvalues and eigenvectors is pretty much important. So let's calculate about the Jordan normal form, how it is calculated, all those things. The very first thing is, like in previous slide I have shown you the matrices. So if there is a matrix which is in a complex structure and you want to convert it to the diagonalized, knowing that it may be diagonalized properly or it may not be diagonalized that well. So the thing is, it's not a complex. I'm telling you again and again. It's just a form where you write a matrix in an easier way that's near to a diagonalized form. So, how exactly the Jordan normal form is calculated? First, we get the eigenvalues of the vectors from solving the equation of determinant of a minus lambda I equals to 0. We get the value of eigenvalues. The eigenvalues make them distinct, or also make them single. Depending upon the eigenvalues, we can also get the eigenvectors. Don't worry, the example will be shown in next slide. So like that, we get the eigenvalues, we get eigenvectors, and depending upon how many independent eigenvectors and eigenvalues is there, Jordan normal form is formed, and that form is called Jordan blocks. So like if you are not that hearing about the eigenvalue equation, how to actually find it, you can find the eigenvalues using the equations. Determinant of A minus lambda I, where A is the matrix itself and I is the identity matrix. You solve it and you will get the eigenvalues, and similarly just with the right hand side equation you can get the eigenvectors. So let's go for the Jordan block. Suppose there is a matrix, right? Imagine a diagonal matrix. In a diagonal matrix, every element in the diagonalized form is non-zero and every other is zero. However, in Jordan normal form, it's not exactly fully diagonalized, meaning the diagonal elements are non-zero. Like that's basic, but there are one that appears in the super diagonal form. Why it occurs? It occurs if there is dependent eigenvectors. Like if when you calculate eigenvalues, you may get repeated eigenvalues, right? And if the repeated eigenvalues points towards the same eigenvectors, we will get a dependent eigenvector. Like if it's a 3 by 3 matrix and you get the eigenvalues, suppose 2, 2 and 5, you see there is 2 eigenvalues, and if the both two eigenvalues represents a single eigenvector, we have just two eigenvector independent in that matrix, right? So 3 by 3 matrix with two independent eigenvectors, that's not sufficient, so one appears at the side of the repeated eigenvalues. So let's see what a Jordan block is. Jordan block is the finalized or the final form towards which is near to a diagonalized form converted from the original complex form, right? It can be 1 by 1, it can be 1 by 2, it can be 3, sorry, my mistake, it can be 1 by 1, it can be 2 by 2, it can be 3 by 3 too. One Jordan block equals to one independent eigenvector. Here's the example of the eigenblocks. You see there are one that appears above 3, 3, because let's see the example of 3 by 3 matrix as the size 3. You see all the diagonal elements are 3. I have told you every element in the diagonal values are eigenvalues. So when you were calculating the eigenvalues of a certain complex matrix, you got 3 eigenvalues which were repeated, 3, 3 and 3, and those each eigenvalues pointed towards the same eigenvectors, so the one appears above, and the one appears at the super diagonal as a super diagonal elements. Now let's go through as the example. You will understand it much quicker. For just revision, I'll advise you a certain thing to keep in your mind. It's not a complex thing. I'm saying it again and again. It's just a way to write a square matrix in such a way that it will come in the nearest diagonalized form, so that it would be easier to compute with. Just the change of form, nothing else. And the change of form is done by calculating eigenvalues, calculating eigenvectors, and the Jordan block is formed based upon how many independent eigenvectors are there. The diagonal elements in a Jordan block represents eigenvalues, and if there is same eigenvalues and they represent same eigenvector, the one appears in the super diagonal element. So let's consider a matrix. Here's a matrix 4 1 minus 1 0 2 1 0 0 2. You can see this matrix, it's not in the diagonalized form, and to get the best form you go through the Jordan normal form. So as per the rule, you find eigenvalues and eigenvectors. So you find the eigenvalues comes as 4 2 2. In the left hand side in the step 1 you can see the eigenvalues, it's been calculated, the equation, and that came is 4 minus lambda equals to 2 minus lambda square equals to 0. This comes from an equation of a minus lambda I by finding its determinant equals to 0, right? So the eigenvalues you get out of this matrix is 4, 2 and 2, and while finding the eigenvectors, solving the equations by keeping each eigenvalues, the repeated eigenvalues 2 and 2 points to the same eigenvectors, so there is a dependency of eigenvector. So obviously in this time 1 appears. It's not a pure diagonal form, so it's written as in the final form. Like you can see the matrix before, 4 2 2 1 1 minus 1. Going through the equation to find eigenvalues and vectors, you get there is the dependency in the eigenvectors. So you take all the eigenvalues, which is 4 2 2, and place in the diagonal element. That's the first step. And there was a 2 2 a repetitive eigenvalue 2 and 2, and since the 2 and 2 represented a single eigenvector, the 1 will appear in the super diagonal element. That's it. No, nothing complex. Now this is the easiest final form, nearest to diagonal form, which is a Jordan normal form that you can work with, compute with, and it is very useful where you have to deal with complex matrix form. So for the proper understanding and for this concept, it's an easier one. I'll repeat it in a summarized thing. What is Jordan normal form? Suppose there is a matrix form which is complex and needed to be compute with or work with. Jordan normal form is introduced to convert that form of a matrix to a Jordan block, which is closer to our diagonal matrix, right? The sole purpose of this concept is to change in a nearest diagonal matrix so that it will be easier to compute with. And suppose there is a complex matrix, the first step you do is find eigenvalues, and you count how many independent eigenvalues are there. Like you may get 4 2 2 eigenvalues or 4 2 3. If you get a 4 2 3 eigenvalues, of course you will be getting distinct 3 eigenvectors, and it will be a pure diagonal form. However, if you get a 4 2 2 where there is a repeated eigenvalues, you will get dependent eigenvectors, and where there will be repeated eigenvalues, a 1 appear to balance that, and it will be a closer to a diagonal matrix where it will be easier to use it. So that's it, just a better form than a usual complex form for a matrix, so that it could be analyzed, it could be computed relatively easier. So for the proper understanding and for this concept, it's an easier one. I'll repeat it in a summarized thing. What is Jordan normal form? Suppose there is a matrix form which is complex and needed to be compute with or work with. Jordan normal form is introduced to convert that form of a matrix to a Jordan block, which is closer to our diagonal matrix, right? The sole purpose of this concept is to change in a nearest diagonal matrix so that it will be easier to compute with. And suppose there is a complex matrix, the first step you do is find eigenvalues, and you count how many independent eigenvalues are there. Like you may get 4 2 2 eigenvalues or 4 2 3. If you get a 4 2 3 eigenvalues, of course you will be getting distinct 3 eigenvectors, and it will be a pure diagonal form. However, if you get a 4 2 2, where there is a repeated eigenvalues, you'll get dependent eigenvectors, and where the there will be repeated eigenvalues, a 1 up here to balance that, and it will be a closer to a diagonal matrix where it would be easier to use it. So that's it, just a better form than a usual complex form for a matrix, so that it could be analyzed, it could be computed relatively easier.